So good evening and good morning in Bangladesh. Welcome to our ABIA technical seminar session. Today we are very fortunate to have among us Dr. Francis Tanzella. Before I give his brief introduction, let us introduce ourselves that we are here. I'm Anis Rahman, Seminar Chair for American Association of Bangladeshi Engineers and Architects, or AABEA. And we have Dr. Sufyan Khandekar. Sufyan, please say a few words.
Okay. Thank you, Anis. Thank you, the keynote speaker. I'm Sufyan Khandekar. Professionally, I'm a civil engineer, geotechnical engineer. I have worked on the nuclear power industry for 29 years, so I have some knowledge to that. The reactor that was built in Princeton for the fusion reactor, we are involved on that. So some basic knowledge there. I also was the former president of ABIA Central and the founding president of ABIA New York chapter.
Mr. Tarek.
Hi, good evening, everyone, and good morning in Bangladesh. Yeah, I'm A.K.M. Tariq, and currently I'm serving as a secretary for the ABS Central. And professionally, I'm working for California Department of Transportation. We call it Caltrans, and I've been here with Caltrans for 25 years. So here as a transportation engineer, registered civil engineers in California. Yeah, anything with the freeway, that's what we do. And prior to that, I was working as an environmental engineer and also was a faculty in back home, Bangladesh University of Engineering and Technology. Thank you.
Thank you, Tariq Bhai. Professor Afzal.
I'm a chemist by training, and I taught at Truman State University for many years. And currently, I have the status of a professor emeritus, and I'm no longer doing any research because I don't have a lab, but I would like to be engaged with some activities in the future.
Thank you. Shabir Bhai.
Oh, hello. This is Shabir Pervez. I spent my lifetime working on designs of satellites. My primary expertise being in guidance, navigation, and control. Although these days I have a small company, we are working on more efficient power amplifiers for satellites, RF communications. So that's what I've been keeping me busy lately. Looking forward to your talk.
Muhammad Asif. Are you there?
Yeah, hi, this is Muhammad Asif. I'm actually an industrial engineer. All my life, I work in the automotive industry, pretty much everywhere from Australia, Japan to US. So currently, I'm actually doing turnaround for basically distressed companies, merger, acquisition, and so on. I'm based out of Michigan. Thank you.
Wonderful. Nizan Bhai, are you there? You want to say hello?
Yeah, sorry, I'm here. Yeah, my name is Mizanul Chaudhary. I work for MIT Lincoln Laboratory as well as MIT campus. So Lincoln Laboratory, I'm mostly involved with telescope, James Webb Telescope, and also satellite. Tomorrow, my work will go to space, tropics satellite. And at MIT campus, I'm mostly involved with the MIT Zero Robotics. This program runs inside the International Space Station. It is a educational program for middle school and high school, and also it is a PhD project. Basically, we teach how to code International Space Robot, which helps astronaut inside the station. So students learn how to write code. And before MIT, I worked for DoD for 10 years in the cybersecurity domain. That's all I have. Makes me. Thank you.
Wonderful. Thank you. And last but not least, we have Ashik, who is an environmental scientist. Ashik, you wanna say something?
Hi, good afternoon, everyone. This is Ashikur Rahman. I'm currently working at the Pennsylvania Department of Environmental Protection here in Harrisburg, Pennsylvania. Glad to meet you all. I'm sorry I could not turn on my camera. It's malfunctioning. And I previously worked with nanomaterials in my PhD and in the overlapping areas of nanomaterials and water treatment. And I recently got in communication with Dr. Ranis. I thank Dr. Ranis for inviting me to attend this meeting. This is actually my first time appearance in the AABS seminar series, and I look forward to attending more in the future. Thanks, everyone.
Thank you. And now let me say a few words. We are really fortunate to have Dr. Francis Tanzella to talk on this very complicated subject of low energy nuclear reaction, but he has magic in his talk, as you will see in a minute. Dr. Tanzella is the past program manager in charge of low energy nuclear reactions at SRI International. He is actually one of the handful scientists in the world whose contribution led to a successful demonstration of LENR effect in layered tubes. He earned PhD from UC Berkeley and did postdoc at UPenn. And then he worked for DuPont. And then he joined SRI, where he used electrochemical techniques to monitor chemical reaction rates in many processes, including hydrogen and palladium. Dr. Tanzella has helped develop the LENR electrochemical and calorimetry program at SRI. His expertise extends beyond the measurement and control of hydrogen palladium LENR reactor to include electrical, electrochemical, and acoustic simulation. Acoustic stimulation of the palladium hydrogen system to yield LENR process in solids. In addition, he developed different experimental nuclear measurements to determine the presence or absence of nuclear particle in LENR processes. His reproduction and modification of palladium hydrogen co-deposition process was able to assure that cracks produced in the chromium-39 solid-state nuclear crack detectors were not of chemical origin, but of nuclear origin. He has hosted many LENR researchers in attempts to reproduce and understand their processes and devices. Dr. Tanzella has published more than 75 papers in the field of LENR and related subjects. He is a proponent of displaying the extension of existing plasma fusion theories to LENR and finding overlapping hypotheses when possible. With that, it is my extreme pleasure and honor to present to you Dr. Francis Tanzella.
All right. Thank you very much, Honest. That was very kind words. So let me see if I can get my PowerPoint up and running according to the instructions. Yeah, we go here, share. Then we go here and do that. And okay. Can everyone see my slides?
Yes, you can see it.
Okay, so the system is working. Okay, so yes, I'm very glad to be here. Look forward to hopefully some nice discussions. As you can see, I left SRI in 2018 after 32 years, started a small meaning a single member LLC called the Energy Research Center. And I have a small laboratory about 2 miles away from my house with a fair amount of electrical equipment and surprisingly germanium gamma spectrometer and a couple of things like that. And I will not talk about that since nuclear measurements are not my expertise. And like I mentioned, my training was actually in synthetic inorganic chemistry. And let's go. Okay, choose down. Okay. LENR background. On March 23rd, 1989, Fleischmann and Pons reported results of their work pretty much at a press conference, which was very uncommon, but it was an electrochemical reaction with heavy water, D2O, with lithium in it and palladium cathodes, so that the deuterium was depositing on the palladium. And it was well known that when you deposit that sort of palladium, that sort of deuterium on palladium or any hydrogen isotope, it absorbs in and diffuses into the palladium. It was at a level, the heat effect that they saw was at a level consistent with nuclear, but not chemical energy or known lattice, but occurred mostly without any penetrating radiation. And the nuclear level effects observed in the system have been 100 to 1,000 times more energy than known chemical effects. This is when they're integrated over time. So we're talking energy here. Time for my first story. It just happened. At the time, we were working on measuring hydrogen in primary coolant in fission reactors, mostly Westinghouse pressurized water reactors. And one way to do that is with palladium. So we had a device with palladium wire inside a letdown line at a fission power plant, specifically Turkey Point in Florida. And we were measuring the hydrogen present. Hydrogen is added to counteract the oxygen to prevent oxidation, but you then have to measure the hydrogen to prevent hydrogen embrittlement. So it's a very difficult, convoluted method they were using at the time, and this one was much easier. Now, we couldn't get real access to primary coolant. Like I said, it was a letdown line. So Mike McCoubry, who was my program manager at the time, called up one of his buddies in Chalk River, Ontario, and he was up at Chalk River testing our device on the day of the March 23rd announcement in 1989, which is very interesting because when Pons and Fleischmann were announcing deuterium or cold fusion in D2O with electrochemical methods, we were actually using palladium. We were actually passing current through palladium in one of the Canadian CANDU reactors, which uses D2O. So we felt pretty confident that maybe we knew something about it. In addition, Mike McCoubry had actually spent time with Martin Fleischmann and Stan Pons when they were both in England. And of course, after the press conference and the American Physical Society meeting, Steve Jones, who at about the same time claimed muon catalyzed fusion, there was a large controversy and a lot of debate going on. Oh, I guess at this point I should mention that I have plagiarized a lot of slides from a lot of my friends, and I will apologize to them next time I see them. And this one is from Dave Nagel. Okay, early studies, yes. One of Mike McCoubry's favorite saying was, "To a man with a hammer, every problem looks like a nail." And what that meant in this field was, yes, there were a bunch of electrochemists, but that wasn't everybody. And I'm talking immediately, the first 1 to 3 months, there were people trying all kinds of alternative methodologies. Instead of palladium, using nickel or titanium and light water and even non-aqueous, and then instead of lithium, different alkali metals, and then using gaseous experiments with either deuterium or hydrogen and those same metals. Electrical discharge underwater, D2O, low energy plasma arcs in gas phase, sonochemistry, sonofusion, sonoluminescence, high voltage pulse stimulation. And this is only a small example of what everybody did at the time. And this is just a graphical version of that slide that I just gave, which is probably a good time for another story. We were originally, well, the original hydrogen measurement was funded by the Electric Power Research Institute. And so Mike McCubry asked the contract monitor, Tom Passel, okay, this is a really interesting topic. We're experienced in it. Can we take a little bit of money and some time away from this project and work on cold fusion? And Tom Passel agreed. And yes, Mike always is embarrassed to say that he thought we could solve the problem with $50,000 in 3 months. So here we are 34 years later, and I think SRI spent upwards of $10 million on it. But another story, because this was EPRI, we would go over there all the time. It's just 5 miles away from SRI. And we would go over, and I remember in the early days, probably within a month or two in it, one of the EPRI scientists asked a question in analogy. He asked whether it was 1909 or 1939, trying to find out, okay, was it Rutherford back when he first saw the new particles coming out of nucleus and 50 years away from a practical fission reactor? Or was it 1939 when Fermi pulled his simple control rods out from his carbon reactor and saw excess heat, and it was only 20 years away from that first fission reactor? Well, obviously it was not 1939, and we just hope it was a lot closer to 1939 than it was to 1909. Okay, just to give you an idea that this is international, this is a quick list of all the countries that have in the past and still do work on it. Whoever made up this list, I will have to, yes, tell Dave Nagel that he forgot Canada. Anyway. And this is a slide I gave, as you can see, 6 years ago. So not all of these people are still working, but this was the people in North America working on it at the time. And you can see there were people doing research, people presenting funding, people trying to commercialize, and people working on mechanism. And my friend down at the University of Texas, who was working on legal, he actually was at the LBJ School of Law at the time, has now moved on to archiving data and working on the history, but not this sort of history, the history to collect all the information necessary that people working in the field could use years from now. So back to SRI, since that's most of what I know, we did some important things in our measure. The deuterium palladium loading in the electrochemical system was not well known. A lot was known about hydrogen up to an extent, but nobody knew about deuterium up to very high loading. So we did a lot of that, and I'll present a slide on that. And we worked with chemical additives, poisons, and then, of course, a fully automated flow calorimeter, which I will show a figure of. And then about 2000, we decided, okay, there's a lot of people out there doing different things and we can't do it all. So we invited certain people to come over and to work with us to show us what they were doing. And we had a protocol. If possible, the researcher would come over, run the experiment their way. We'd look over their shoulder. Then we would run the experiment, hopefully their way, while they were looking over our shoulder. And then they would leave and we would run the experiment on our own and start tweaking the knobs. And this is an example of some of the ones that we did. And I'm going to talk about probably two of these. And there's that resistance ratio versus loading function. So if you find out early that you need to be 0.9 deuterium to palladium, then this chart tells you when you can do a resistance measurement where that is, so you know whether or not you're there. And we used it regularly. We had online 4-terminal AC resistance measurement in all our DC electrochemical cells. And this is an example of our best early calorimeter. As you can see, it had a thermal efficiency of over 99% and an absolute accuracy of plus or minus 0.33%. And it's rather convoluted. And Mike McCubry used to like to joke that we dragged the calorimetry methodology out of the 19th century and at least into the 20th, if not yet into the 21st century. And this is different than most of the calorimeters that people use. They used to use bomb calorimeters for measuring energy coming out of a very fast reaction. Whereas this is a slow, some of these experiments take months. And another one of our experiments, well, let me stop here for a second and interject. In plasma fusion, people are taught that there are two branching ratios, generally the one to tritium or the one to helium-3. But people will admit that there is a third one, but those first two are split pretty much evenly at 50%. And then there's one down several orders of magnitude, which is shown here, which is a direct reaction into helium-4 with a 23.8 MeV photon gamma coming off. And so in one of our experiments, we had two experiments that were sealed. In this particular experiment, since it was sealed well enough, we can measure the helium in the headspace and talk about the excess energy that was measured. And so on the left is a chart which shows the measurement of how much helium was in there and how much energy. So the helium's along the left axis and the energy is along the right axis, and they more or less follow each other. So if you were to plot all of those on the right side with energy in kilojoules, integrated energy, versus the helium increased concentration, you see something that you could draw a straight line through. And when you take the slope of that line, you end up with a number either 31 or 32 MeVs with some very large error bars. And we always felt that we just didn't get enough helium out of the metal in order to get it closer to 24 MeV. Now, it may not be 23.8 MeV because the method and the mechanism is going to be different inside a lattice than it is in a two-body reaction. And I'm not going to talk about mechanism. Like I said, I'm trained as a synthesis chemist and spent most of my career as an electrochemist. I leave that to others. And fortunately or unfortunately for the field, there are at least as many mechanistic hypotheses as there are researchers. One of my good buddies, okay, that wasn't going to go there. Anyway, one of my good friends just had a conference call with Peter Hagelstein in the Radio Laboratory of Electronics at MIT 2 days ago, is one of the people with one of the better mechanistic hypotheses that I agree with. So this was another pseudo electrochemical experiment. If you look down in the bottom right, you see there's essentially a palladium bottle filled with palladium black nanopowder and sealed with a high pressure. And so what happens if you put that as the cathode, an electrochemical cell with lithium deuteroxide or lithium hydroxide, you actually deposit the hydrogen isotope on the surface of the bottle and it diffuses in to the palladium black. And now you have an extremely high surface to volume ratio, so you can get a very high deuterium to palladium ratio. And we ran that experiment for a month, and I don't expect you to follow all of this, but the blue line down there, which is the straight line come out of the green dots, is the excess power that came out of the light water experiment. And the red line, and the purple line is the best one through the heavy water experiments. You see has quite a bit more energy. But well, power and energy. So that proved to us that there's something about this methodology that can actually perform the electrochemical Fleischmann Pons effect. But since it was a sealed bottle, we wanted to look at what the gases were in it. So we sent it up to McMaster University in Canada, and Brian Clark sliced it. So this is a slice out of one of the across this, and this is a quadrant of that slice. And he got 7 pieces out of it and measured the helium-3 and measured the helium-3. So you see very close to the middle had a very large helium-3 content, but as it gets towards the outer wall, it's down by a factor of 4 or 5. And the hypothesis is that created tritium in the palladium black, and then it diffused out as hydrogen does through these different layers. But it took so long that the tritium actually decayed to helium-3. And that's how you get this helium-3 decay pattern. Okay, now another experiment we did at SRI, and there isn't a whole lot you can see here, but this is an electrochemical cell. On this side is the anode, platinum anode between these 2 magnets, and in there is the cathode, which is generally either palladium or nickel, and then a palladium chloride, lithium chloride solution in heavy water is in there, and it's slowly deposited over here. The palladium deposits first, and then during the palladium deposit, some of the deuterium deposits on it, and that continues on. This takes weeks, and you do it slowly enough, you grow a very nice crystal structure. And behind that is a 25 micron mylar film. And behind that film is a piece of CR39 solid state nuclear track detector. This is a technology from 50, 60, 70 years ago before people could afford expensive gamma spectrometers, etc. And we were actually looking for alphas since people had reported those in the past and we had seen helium-4. But this was sent over to a coworker in Moscow who analyzed it and actually did many more etching experiments on it and did a fair amount of calibration and proved it was protons, that protons were causing those tracks. And this was published in the International Journal of Hydrogen Energy, and there's a DOI reference there for anybody who's interested. First, I'll take a second and talk about Brillouin Energy. Yes. Among all the people we worked with, there are many more, but Brillouin Energy is the only one that was in the Bay Area. They're in an off-campus startup in Berkeley, and they came to us asking us if we could look over their calorimetry. And we did some of that, and I've given talks about it, and we've published it. But this, we were trying to find out what the nickel looked like. What they have is nickel is sprayed on an alumina coating, and there's a return copper underneath that. And I have to be careful what I do with my mouse. And we wanted to see what the nickel looked like. So we sent it off to Anis Raman, and he performed his magic with his terahertz lattice scale imaging. And these are the results. And unfortunately, I wasn't able to get the animation working, but these lines show the lattice spacing. And the imaging showed the lattice spacing was 0.45 microns versus 0.35 microns for pure nickel, which gives you a calculated density of almost half. And so there is a 100 by 100 nanometer image. And then there's that very nice 3D perspective image, which unfortunately is not going to rotate today. But down in the bottom right corner is the Fourier transform analysis where you calculate the lattice spacing. And that's all I know about it. If you want any more, you can ask Anis. And while we were at it, and there's the reference, while we were at it, we had Anis do some spectroscopy, same stuff. And there's the setup. If any of you don't know how his equipment works, feel free to ask Anis, not me. And it's a frequency domain of absorbance was collected in the terahertz region. And so there are 4 different samples there. And then there was also a close-up, which I didn't show. But the peaks are in the range of published phonon vibrations calculated for nickel. And so that kind of gave us confidence that we knew we were looking at nickel and not something else. Okay. And like I said, there are a bunch of other people working in the field. Okay, so this one is from Ed Storms. He has a really nice Seebeck calorimeter. I don't know how much of you are familiar with Seebeck calorimeters, Zeeman effect. They're just a bunch of thermocouples tied together in series. And this calorimeter, I think, has over 200 of them, totally encasing it inside the insulation. And so you just measure the voltage of all those thermocouples tied together, and that can be calibrated proportional to thermal power giving out. And so you measure the electrochemical or the electrical power going in. Ed Storms has run both electrochemical cells and gas cells with resistive heaters in them. And both of them have resistive heater calibrations. And so what you see down below is a comparison of the electrochemical cells and the gas cells. And the left plot is excess power versus temperature. And you see Ed was able to go to higher temperatures, of course, without the electrochemical cell. But all three of them, even the one with no current, after he turns the current off, show excess power. And then if you plot that versus 1 over T and the log of excess power, you get an Arrhenius plot. And Ed shows that there's an activation energy that you can find for these two different experiments, or two different activation energies with an inflection at about 50 degrees C. Okay. Oh, one of the more recent things is this fellow Frank Gordon. He used to be at a Navy lab in San Diego, worked in the same place with Stan Spock and Pam Mosier-Boss. Oh, I should mention that co-deposition experiment that I did with the CR39 was originally done by Pam Boss, and that reference I gave was probably to the second paper in back-to-back papers in the journal. The first one was with Pam Boss and Larry Forsley, and the second one was with myself and Alexei Rosetsky and the late Andre Lipson in International Journal of Hydrogen Energy. So I'm not going to go through this, but Frank Gordon has done this. He's given it to 5 different labs, and they've all reproduced it. And what you see is a voltage coming out, and if you put a load on it, you can measure the current. And this is just either palladium hydride or palladium deuteride on a brass nipple inside. It's co-deposited, similar to what Boss and Spock did on usually a pretty simple copper wire. Or, yeah. Oh, yes, right. It's brass on brass. It's just stuff you can go buy at the hardware store. And so there's how it's all constructed and how it's sealed. And like I said, 4 or 5 different labs have measured that voltage and current. Now, it's not a very high current at this point, but Frank is convinced that it will scale and it will be part of one of the gas phase technologies used in this field. And okay, there's a lot of work in Japan, as I mentioned. This one again is a busy slide, but as you can see, everything is tiny. If you look in the top right, you see you have this 100 micron nickel with sandwiches of 2 nanometer copper and 14 nanometers nickels, and they make about a stack of 7 of those. And he passes deuterium through them at different temperatures and sees excess power. And this is where it's stacked, and that's how they do their calorimetry. This one is taken a lot of interest recently. Professor Mizuno at Sapporo University has palladium on a nickel mesh in heated deuterium gas. And this one here he has in his living room, heating his living room. with 50 watts in and 300 watts out. So he's showing that something's going on. This one is only 2 hours long. The original work that was done in his living room was 24 to 48 hours long. And then Google spent, believe it or not, $10 million on a bunch of people to take a look at the methodology and the material science and the physics and all of that. And those are the 4 program managers that they funded. Those are the institutions represented in their groups, since, you know, none of this is done by 4 program managers. So down below, I think Matt Trevithick, who was the program manager running this at Google, said there are 27 people involved in this work. And the bottom line is they didn't see excess power, but they put together some very good technologies that can be used to look for excess power and nuclear effects. And they published it all in Nature Perspective, which is good because it means other people can get in the Nature Perspective. The US Department of Energy has taken notice, and they've put out a program. Some of them are the same. You may recognize the name. Thomas Schenkel was in the Charleston project. He just got an award. There's a fellow at Stanford who I've only not yet met, but he's nearby, obviously. And then one of those, the 2 that are labeled Cat B, means category B, they're doing measurements for the other 6 people. And I don't want to get into much of the detail here. The work at MIT, Florian Metzler, who's in the same group as Peter Hagelstein at RLE. And any of you at MIT are more than happy to contact Peter or Florian. Here's a summary by my friend Dave Nagel. Nuclear reactions can be caused, thermal energy is measured, can't be explained. You get that 2,000 EV per atom, and products that cannot come from chemical reactions, tritium, helium, and a lot of other people have seen other things. And there is a short bibliography if any of you are interested. These are places that you can look for any of the information. It's out there. Jed Rothwell runs leonardcanner.org, and he has probably 5,000 or 6,000 references in his bibliography now. And I'll thank all my people from whom I've plagiarized, and I thank you for your attention. And ready to take questions.
Wonderful. Well, I think you made a lot of shortcut, but we did learn a lot, particularly that the energy that's coming out cannot be from chemical reaction. It is of nuclear nature. So with that, let us open the floor for questions.
I have number 1 question.
Yes, please.
Okay. Is there any, since I'm working mostly with the space technology, is there any experiment on the space related nuclear?
Yes, I couldn't get everybody in. It's not an exaggeration to say that there are 100 different groups probably doing 50 different methodologies. But one of those groups is at NASA Glenn. And I don't know if you're familiar with their work.
I'm familiar with that, yeah.
Teresa Benyo and Gus Freilich and Larry Forsley. To my mind, that's probably the only people who are public. There were people at Langley, NASA Langley, but I haven't had any contact with them in a while.
I see. Okay. And I have another question.
Yeah,
Sorry.
please.
So I'm involved with the NASA working group on International Space Station.
Mhm.
Is there any test can be done in the station related to this type of experiment?
An interesting one that I've always thought of, palladium in particular, when you put hydrogen isotopes, deuterium or hydrogen into it, the crystal structure expands by 7% in all directions, and the volume increases by, I think it's close to 40%. And it'd be interesting to see how that worked in
Microgravity.
Yeah, microgravity. Yeah.
Oh, that will be very interesting. Yeah.
And
Because some of our
I'm
yeah.
sorry, go ahead. Go ahead.
Sorry, some of our astronauts, they're interested in microgravity, testing this type of stuff in microgravity.
Okay, I'm sure if I bring it into the field, yeah, because as you know, the people at NASA Glenn are working on propulsion.
Yeah, the reason I'm asking that if you're interested, then we can submit a proposal to the International Space Station National Laboratory. So they will set up the test bed for you.
Hey, I'll put a note out. There's a news group that has about 400 people, and well, 2 or 3 news groups, but the one I spend most of my time with has, 300 to 400 people, and I'll put out a note to see if any of the researchers there have ideas that they feel would gain by use in microgravity.
Sure. Thank you.
Yeah, thanks for your question.
So if I may interrupt a little bit, because I see that 2 of the scientists from BAEC have joined us from Bangladesh. One is Dr. Tariq Chaudhuri, other one is Dr. Tabirul Hassan. So it's actually Tabirul is the one who initiated this this initiative. So if you Tabirul or Tariq, if you wish to turn on your camera and introduce yourselves and then say something, or if you have a question.
Hello, thank you for giving me the floor. I'm Tabirul Hassan. I really appreciate for you, the expert on this field, to take time and discuss this topic in front of us. From me, I can say that I'm really interested in the topic, and I have learned so many things, and I have understood that there are so much to learn for me from my field, where am I right now. And I really wish that I could work on this project and take guidance from you. Thank you so much. Thank you so much for giving me the floor, and I'm giving you back to it.
Okay. Yeah.
Thank you, Tabirul. And Tariq, I have not met you yet. So if you want to turn on your camera, maybe, or if you have any question, but introduce yourself, please. Your microphone is not working. So anyway, I will mention that Tariq Chaudhuri. Is it working? So he is a chief scientific officer at Bangladesh Atomic Energy Commission, and maybe we can connect later at a time when Tabirul and also Tariq. Yeah.
Can you hear me?
Yeah, we can hear you now. Go ahead.
Okay. Thank you. Assalamu alaikum, Dr. Anis. My name is Muhammad Tariq Chaudhuri. I have a physics background, and I'm basically working on solid state physics and semiconductor thin film. And recently, I'm working on nuclear accidental analysis, especially it is related to the atmospheric dispersion model. In my early career, I worked on condensed matter physics theories like graphene semiconductor device and like this. So thank you very much, Dr. Anis, for giving me the opportunity to introduce this new field to us, and hopefully we will work together in near future. Thank you very much, and thank you very much for your nice presentation.
Thank you, Tarek. We will try to tap into the expertise of Dr. Tanzella in the future, and let's see if some collaboration can be developed. We'll talk about it. So let's go.
Yeah,
into
yeah,
the
we will talk about
question now. Sufyan Bhai next.
Thank you, Anis. This is a little above my experience and expertise. The only thing what I could understand that there is a lot of concern that LENR is it a myth or is it the real thing? Obviously, there are two schools of thoughts. Reciprocity of the same test has not proven beyond doubt that cold fusion is possible. DOE has a different opinion. They have concluded that that is most likely is not possible. The only mechanism has been, the best example of fusion is obviously the sun or the star, and that requires tremendous heat and pressure. And that's what everybody is trying to do. Recently, you probably saw that there was a success at that they could generate almost 50% more energy input output for a very limited time. And that's where they're putting their money now, that if this can be sustained, that is a feasibility in maybe another 20, 30 years, 50 years, that fusion may be possible. What is a proven technology, as we know, sun or any other star. High temperature and high pressure can fuse those atom deuterium together in an electrolysis method. Still, there are lots of questions that at least I don't understand, and I have a limited knowledge to begin with, I have to say. So it is still, it could be an option if it, most of the times the experiments, what I understand, could not be repeated. And that does not give very good confidence that this is a methodology may produce energy through cold fusion. So it's still more question than answers. So maybe it is right, maybe it is not, but of course we will only know once we have exhausted all our experimentation and we have proven that it is a sustainable either reaction. It is being told that it is not only chemical reaction, electrolysis, but it is causing some kind of a nuclear fusion. So how do you prove that? Those are a lot of questions. But at this point, I think the world community, those who are working on the fusion energy, they are more interested on the method of, but there are two methodologies has been looked into. One is a laser-based and one was magnetic. Tokamak was in Princeton. They pretty much gave up. The Princeton reactor, we actually built it. I used to work for Raytheon Engineers, the constructor at that time. So they pretty much gave up on the magnetic concept. Now they are pursuing on the laser, concentrated laser, may be able to fuse the two molecules, deuterium and generate the energy. And recently they have been able to prove it successfully for a few seconds. So that is the most immediate hope that probably that will come much faster with the resources available and interest shown. So we from our community think that that might be a more viable, more provable technology. In a LENR, we have a lot of questions not answered yet, but you cannot just discard it on that ground that it could be an alternate methodology, but we are not at the stage to say that this is a viable technology will give us a result in a short time. At the same time, I saw one gentleman from BIAC. I understand that you must be working on the Rookwood nuclear power plant. I don't know, you know me or not. I serve as the advisor, outside advisor for the Rookwood nuclear power plant, but my expertise on the water area, cooling water systems. I have been designing cooling water systems all over the world. Working on the nuclear field, I studied nuclear energy. That was my minor for my doctorate. I understand the mechanism of the fission, not fusion. So fusion is a great, if it can be achieved in our lifetime, that will be the greatest achievements of this century. There is no question in my mind that that solves all the concerns we have, radioactivity, all those kinds of, and infinite energy source. If it can be solved in our lifetime, that will be the greatest, as I said, achievement of this century. Thank you again for the speaker. I'm very grateful. I learned a lot of things. Dr. Tanzella very nicely presented the concept. Before I didn't understand anything about this methodology. Now at least I have some basic idea that how it works. It is primarily we're saying is that the petroleum is absorbing those deuterium diffused into the and goes into that, in that somehow either electrolysis or through some other mechanism producing more energy than it is required, which is a good sign if it can be done. Thank you.
Tanzella.
You're welcome. Two things. One, the Department of Energy is hedging their bets. The one slide I showed, ARPA-E, as part of Department of Energy, is just let a $10 million program to 8 different groups to study LENR. And they've set the bar a little higher or lower, depending on your point of view. I believe that a lot of people working in this field are moving to higher energies, and a lot of people working in plasma fusion are moving to lower energies. So ARPA-E set the maximum input energy at 500 keV. And I look forward to both of those groups getting closer together. The mechanism, like I said, there are at least 100 different mechanisms being discussed. It's almost impossible to prove any of them. The one I trust the most from Peter Hagelstein involves resonance of, say, 1 billion atoms. And instead of having the excess angular momentum interact with the photon field to give you a gamma, the excess angular momentum from the energy given off interacts with the phonon field to excite the atoms and give off heat. And for reasons not totally known, the branch that works inside the solid state is primarily the helium-4 branch. That's based on a little bit of data.
So if I may add a little bit, I had a discussion with Robert Godis, of Brillouin.
Mhm.
So like you mentioned that phonon. So the Brillouin zone, which is specialized, the unit volume like structure inside that palladium, or in the sample that we worked with was nickel, right?
Yeah.
So he mentioned to me, if I remember correctly, that under certain conditions, the phonon's density goes way up, spike, singular function almost. And that phonon energy can initiate the transfusion. They're not transfusion, what is it called?
Well, his first step is electron capture. And then by a proton to give a neutron, and then the neutron gets captured by more protons until he makes H4, which is not been at least stabilized anywhere, and that decays to helium-4. Now, his is one of 100 hypothetical mechanisms out there, and he doesn't have the time or resources to prove or disprove it, but it keeps him going.
Now, the Burlingame paper that you mentioned, I read that one, and I also, the Yetmeng Chiang of MIT is actually a ceramic guy, which I met in a ceramic conference. So, I mean, they're credible people, but Burlingame paper, of course, had refuted it, that, all the evidence they found, they didn't see any evidence of low energy nuclear reaction. So question is, if I am an investor, which I'm not,
neither am I.
why would I put money in this when I mean, it's not like a situation like when Noah was making his ark on the dry land. He was at least making something, right? It was an ark. Too early, but still. So can you make the case, please, for me, that why government or citizens should put money in this thing?
Well, because energy around the world, everybody needs more than one answer. Fusion is not going to solve it. Solar, wind, hydro is not going to solve it. So it's going to have to be, money will be put in to very many baskets. And if it's not government, it will be private investors.
But the data so far, I have seen reports of very positive data. One of the Carl shared an Indian paper with me. They showed the excess energy in MEV, which is very readable. And some of your work that where you applied the RF field, and I saw one paper or plot, I forgot, that shows energy, much excess energy than the energy being input. So why cannot this be a concrete evidence?
It's a materials issue. It's the same as the plasma fusion people have, except our material is the active material and the plasma fusion people have containment issues. But, it's still a materials issue. And you're getting them. We don't know what we need, so we keep trying. The Brillouin experiment is so complicated and resource intensive that nobody else is trying it. So it is just one group. Nobody is attempting to reproduce it. I'm hopeful that of the 6 groups that are funded by RPE to do this, will do some reproduction and will use the resources. I have to emphasize that DOE decided, or RPE decided, to emphasize nuclear measurement, nuclear products, as opposed to excess heat in all of the studies that they funded. And those are just starting. They're still putting their labs together.
Wow, it's very interesting conversation. Asif bhai, you have anything to add?
You asking me? Or somebody
No,
else?
Muhammad Asif, if he didn't say anything, I mean, do you have anything?
Yeah, I listen everything very intensely, even though I'm not a nuclear physicist. I manufacture vehicles and very much on the practical side, but energy is a very big thing. There's a lot of different development going on in the battery technology and others, but definitely we need energy. We need a lot of it, energy, a lot more. So and Dr. Tanzella, you described a lot of the things, and I obviously did not get 90% of it, not expected either, but I could understand where you're heading. The question I have is that obviously as an alternate energy fuel or going from fossil fuel to solar energy or wind energy, still none of these two are enough. And even with the battery technology, we haven't even talked about disposal of all those chemicals and all these batteries, recycling. They would all need energy. Even making an electric car requires fossil fuel to make all that stamping, the plants, steel and everything. So it's not really zero emission when you look at all that. So there is really no other alternative but going for cold fusion environmentally. And I think the other gentleman explained very well, the sun is a good example. So my question is that, is there enough funding that's coming from the government or appropriate bodies to support, to support all the research work and everything? Do you guys feel that, people are really pouring in a lot of money? And I know it's at a very early stage. Everything that we do is always starts like that. So I'm not at all pessimistic about it. So my big question is that, how seriously the federal government or even different organizations putting enough money in the research in this area. Because recently I saw it in the newspaper that, yes, we did get a net energy gain and the global problem is going to be solved. I mean, there was a very upbeat report. But how do you feel about it? Because you are so deeply involved in that. Do you feel that there is enough attention, enough funding is given to do this kind of research?
Not really, but one thing I didn't mention, because like I said, I'm not a mechanistics person, there's another large pot of money has been funding groups in the EU for the last 2 or 3 years. And they're mostly academic, looking at fundamental work. And hopefully enough will come out of that to convince people that we have a mechanism that we can study. But in the rest of the world, like I said, the $10 million that just went into 6 or 8 groups is obviously a very tiny amount. And it's not emphasizing the excess power or excess energy generation. And so, yes, I'm hoping that something useful comes out of both the EU funding and the ARPA-E funding that helps convince both governments and private investors to put in the very large amount of money and organize things in a way that we can move forward. It's not money alone, it's organization. And like I said, there are probably 80 groups active today around the world, but they're very poorly coordinated, except for the EU groups. I think those are very closely coordinated. And hopefully ARPA-E will do something like that so they can coordinate people to have positive results. And right now, people who've been worked in the field for a long time are frustrated because most of the people who got that ARPA-E funding aren't talking to the people who have made excess power for the last few decades.
And I think that was really my point. I mean, my brother was a nuclear physicist at NIST, and unfortunately he passed away a couple of years ago. And he was very much involved in setting up the proton lab at NIST. So I had a privilege of visiting that place. The DOE and the NIST, are they deeply involved with this? And what do you really need to do in order to get the focus on the funding? And I think you touched a very important point, is the organization behind that. So there is a cohesive group that's developing something like this, because I think it's very exciting and it's worth putting every bit of money in it.
Well, I think, like I said, I'm hopeful that the ARPA-E program will lead to results that helps the rest of DOE get interested in throwing, real amounts of money at it. Or even if it's just positive and the government doesn't get interested, I think private investments can do that. And it really only takes one or two champions. And we would have never gotten to this point in ARPA-E without a couple of champions who've come in and said, okay, there's something here. We don't know what it is. We don't know if it can ever be practical, but we need to study it because, as I said, we need all those options in order to move forward and meet our needs.
So my very last question, given where we are today, what's your prognosis in terms of finding an application at the end that solves a global problem with energy? What's your thoughts on that?
I think LENR has a place to be. It may not be, the replacement. Robert Gaddis thinks it's going to replace all those abandoned assets of 0.5 gigawatt coal-fired power plants. Maybe that's not it. Maybe it's a small battery. Maybe it's a backup battery. Maybe it's a transportation battery, or even a transportation engine, an energy source. But I don't know where it is. I just feel that it will have some utility somewhere in the future, even if it's just an analytical tool.
Thank you, sir. Very kind. Appreciate that.
Yeah, you're welcome.
Anyone has any other point? Yeah, Sufyan, please.
Yeah, many questions came on funding and things like that. So, to the best of my knowledge, funding was not the criteria that this research did not advance. When the more accepted technology, which is, as I explained, is the sun for fusion, DOE has funded tremendously.
Mm-hmm.
They have funded 2 reactors, one in Princeton and one in California. One is a laser-based and one was magnetic, high magnet based, and they have funded completely. So funding was not a concern at any point, any research. I was not aware of that. They have recently allocated 10 million is a peanut for DOE.
Oh, absolutely.
If they are convinced, if you can convince them, they will come up with the money. In addition to that, as Dr. Tanzella already mentioned, EU is funding tremendously. Japan is funding. After that, one experiment successful, the whole industry has been very active. As you know, that a lot of the things are being tested in a super collider. At one point, we were building the super collider in Texas, then we abandoned it. In Europe, they have built it already. So money is not going to be the problem for this. Everybody thinks the energy is going to be the biggest problem in coming decades, and that has to be solved. Solar, wind, these are partial solutions. Solar has a problem of storage because it can only produce power when there is a sun. It's half the time there is no sun. So other combination of all those things probably, and the best hope we have is the fusion reactor, and everybody thinks that. And I think in terms of funding is concerned, that will not be the hindrance, as long as this process or the research is on the right path, as long as the government is convinced that there is a hope, they will come up with the money. Of course, the private sector comes a little later. They will, unless it is a venture capital, otherwise like modular reactor, Bill Gates came up with his own money to build the first one. So that will, when there is a technology is available, it is a question of building a reactor, prototype reactor, and generate the power. In those areas, private funding will be more active than on the research side. Research side is normally, majority of the research will come from the government, and I think DOE has a big fund, Europeans has a big fund, and the Japanese are very active also. So as long as they can prove it, the scientists can prove it, that there is a viable solution, they will come up with the money.
I agree, but I have to add, are you familiar with Carl Page and the Anthropocene Institute?
No, I'm not.
Okay, Carl is one of the investors in Brillouin, but more importantly, he and Anthropocene invested in several plasma fusion startups. And he does believe that there is a future, obviously, in the plasma fusion side. Now, he and Anthropocene can't fund at the levels that NIF and JET and those people get, but he can fund these small startups, and I think he's funded 5 or 6 of them. And so, yes, I think there is a place for private money in the early stage, even in the plasma fusion game and in the SMR, the small modular reactors.
Yeah, and to the point of Dr. Khankar is that to take the research shape, one needs funding too. So it's a lot of kind of political or dogmatic thing comes in. Why the making a sun on the earth gets billions of dollars, and why this LENR rods don't get the money? There are a lot in it. So it's not just the results. But anyway, I have one question, Dr. Tanzella, which is, we have here Dr. Tariq Chaudhary and Dr. Tabirul Hassan. They both are from Bangladesh Atomic Energy Commission. If they want to learn more about it or do something about it, what is your suggestion, how they can get started?
Well, first, my slides have been recorded, yes?
Yes, I have recorded it.
The particular, I can bring it up again, but the references on the last page, let me share it again, is a good place to start.
Would it be okay?
Please, please contact me.
Yeah, would you be able to share your presentation today with us?
Yes,
Okay.
you've recorded it, but sure, I can send you a copy of the presentation. And again, I apologize that it was so thin, but it's 34 years and a few hundred researchers. You can't really do it in one presentation.
Right.
But yes, I'll send you a copy of this. And in addition, I'll send a copy of a few links that I give to people who are new to the field to get their feet wet and figure out who's doing what and what. In fact, there's a lot of young people in the field who don't know the history.
Yeah.
So yes, I'll send to you my copy of this, and some of those on the last page there are very good places to start. And the last 2 conferences almost all of the presentations, at least the video of the presentations, are available online. So yeah, if
Okay.
anybody want, and my email is on the front slide, and feel free to send me.
I will share your email with them as well. Yeah.
Right.
Yeah, it's right in the front. Okay.
All right.
So, and anyone has any more questions, please go ahead. Tabirul, did you have any question actually?
Actually, I'm so new to this. I don't have any specific question.
That's okay. That's okay.
Just one simple question that I have seen from from the presentation that there are so many approaches already being done with this topic. So the best results or best hope for is that I remember is the phone interaction with the LENR system. So should we think about approaching specifically that equipment or setup, or should we just study and explore on the other also other?
Well, one thing, yeah, it's a very important question, and you are on the right track. One of the things, all the experiments that you have seen in the references, and if you study, a great majority of them is to sort out if it is electrochemistry or not.
Yes.
So very few actually targeted direct transmutation experiment. So I think a good, and I will ask Dr. Tanzella for his suggestion, but I think that a good place to start is not to, repeat all the others who have tried to refute that it is electrochemistry, etc. No, you start from the hydrogen to deuterium to tritium, and that is the kind of approach, whatever the mechanism may be it phonon, be it the plasma fusion, and which is most likely is the plasma fusion is very promising. And I have some references which I will share with you, but we'll ask Dr. Tanzella if he wants to add anything, please.
Yeah, one of the things that people have kicked around in this field for a while is something they call a lab rat, which is an experiment that's so easy that you could give it to somebody, explain it to them over the phone, and they could reproduce it. There have been several attempts. The one that I showed with the co-deposition of palladium and deuterium and the CR39 is one that's been tried, and that one's relatively simple. The analogy that I like to use is back in '89, for those of you who remember high temperature superconductors, the announcement was at a very similar time frame, and within 3 months, high school kids were operating the shake and bake process and showing the Meissner effect. And so people in cold fusion have been trying to say, well, what can we do to produce that same kind of interest by making an experiment that a high school kid could do?
There we go. All right, so I guess we arrived at the
hello, Dr.
program.
Anis.
Yes,
can I ask something?
Yeah,
Sure.
Go ahead.
Yeah, thank you very much. This is a very illuminating presentation. So a very fundamental problem is that maybe the issue is the material issue. So is it possible to do some experiment with Raman spectroscopy to find a preliminary idea about the criteria of having cold fusion? Just preliminary idea, because I saw some phonon peaks in Tanzella's experimental measurement. So is it possible to have a preliminary idea using Raman spectroscopy that whether this material is suitable for cold fusion experiment? Or
let us talk about it a little later again, maybe not today, but I would recommend that you formulate some experimental study, and we can see if we can convince Dr. Tanzella or some other people to find some sample and you guys get started. We'll work on it. Maybe not to right away, but
Okay, okay.
yeah. But if you can make a proposal, that would be we can discuss with Dr. Tanzella.
Okay, we will talk about it later on. Yes, yes.
Yeah.
If I can mention one thing, one researcher whose work I did not show, Mitchell Schwartz, who, by the way, is a radio oncologist by day, but a cold fusion researcher in the evening, has a Raman spectrometer on his experiment, and he finds an anti-Stokes line that he can identify with one of the deuterium hyperfine structure frequencies.
Oh, that's wonderful. So you are on the right track, Tarek.
Okay, okay, thank you. Okay, we will work on it later on. Yes, okay.
Yeah, if you send me a note, I'll send you some of the references to Mitchell's work.
Yeah.
Okay. Thank you very much.
And thank you enough, Dr. Tanzella and all others. Dr. Sufyan Khandekar is late in the night, and I can't appreciate enough that we had this opportunity to listen to and have this discussion. Skepticism is a part of research process. We are always a skeptic, and that's for healthy reasons. Skepticism is not a bad thing, because unless I'm skeptic about my work or somebody else's, truth never comes out. So, and again, appreciating takes also skepticism. So with that, I thank you all, and this program is recorded, so we'll post it. And with that, good night for today.
All right, good night.
Good night.
Thank you so much. Thank you so much.
All right. You're welcome.